Okay, folks, we are going to get into some familiar ground with a little trip down memory lane here with the individual gas laws, the combined law, and the ideal gas law. Let's do it. So recall the individual gas laws are empirical, right? They were based on these various folks' observations, and generally they're observations under what we now know as ideal conditions. So the first one to talk about is Boyle's law, which states pressure is proportional to 1 over volume. Okay. So in this graph right here, you can see pressure is on the y-axis and 1 over volume is on the x-axis. And when plotted that way, it would make a straight line. Another way that we could look at this is if we just plotted regular old P versus regular old V, we would see that inverse relationship right there. Okay. Another way that we could write this is by saying P times V equals a constant. And once we know what that constant is, we can replace that proportionality sign with an equal sign. Charles' law says that the volume of a gas is directly proportional to its temperature. And we can see here in a graph of volume on the y-axis and temperature on the x-axis, we get another straight line. And of course, by the way, I didn't mention in Boyle's law here, if we're thinking about how this relates to a state function, right, where we have P, V, N, and T all to consider, Boyle's law is only true at constant N and T, right? We had to fix the other two variables there. So Charles' law of volume is directly proportional to temperature, or V divided by T equals a constant. And of course, only at constant pressure and number of moles. Okay. So one that is less talked about, but is still equally important, Amundsen's law, which states that pressure of a gas is directly proportional to its temperature. And we can see that it creates a similar graph as Charles' law, except we replace volume with pressure. Or in other words, P over T equals a constant at where everything else is held constant, right? Let me erase that and write that again. At constant, so that's going to be now volume and number of moles. So notice now with Boyle's law, Charles' law, and Amundsen's law, they all are dependent on constant number of moles and the other variable which is not used. So we need to have some kind of law or rule on what to do with the number of moles. And for that, we rely on Avogadro's principle, which states the volume of a sample is directly proportional to the number of moles, or V divided by N equals a constant at constant pressure and temperature. So in general chemistry, you spend a lot of time going through these different equations and using math to work through the relationships. We're going to skip right past that and kind of look at them in this combined way. So now if we hold number of moles constant, so constant number of moles, we can create this map, really, if you like, okay, this three-dimensional graph of pressure, volume, and temperature. And if we look at various aspects of this, we can tease out the different gas laws. So for example, here we have this isotherm, iso meaning same or constant. So an isotherm is the behavior of pressure and volume at constant temperature. And if we go back and look at the other slide here, we can see that that would describe Boyle's law. So I'm going to write that down right up on top there. Boyle's law describes our isotherms. So now if we look at the isobar, that is occurring at constant pressure, as you can see in the graph. And now that gives us the relationship of volume and temperature. So going back and looking here, we can see that would fit Charles' law, our isobar, okay? And it makes sense that it's an isobar because it's constant pressure, and isotherm, it's constant temperature. And so the last one that we can see there, teasing out Amundsen's law, would be an isochore. And so that would occur, let's see, at constant volume, as you can see right there. Okay, so constant volume. So that gives us an iso, is it CH? It is CH, isochore. I know you want to say isochore, but it's pronounced isochore. Okay. So if we were to combine all of these using all of those proportionalities, we would find the following. We would see that pressure times volume divided by number of moles over temperature must equal some type of constant. Okay. Another way that we can write this is if we allow our conditions to change in some sealed container, okay, where the number of moles can remain fixed, and I'll still write that as N1 for now, okay, then we would see that if we could change any one of those things in our condition, that they would also have to change in this proportional way. So that's what we think of as the combined law. So on the other hand, if we look at this and figure out, well, what is that constant? Using the empirical basis that was determined by Boyle's, Charles, and Amundsen's, we could actually arrive at the ideal gas constant. So PV over N, oops, there it is, I wrote it there. PV over NT equals some constant. We call that constant R, the ideal gas constant, okay? Which we know if we've used ATM, liters, Kelvin, and number of moles, that has the value 0.08206 liter ATM per mole Kelvin. So our gas constant is this constant of proportionality that allows all of these empirical things to be true. Now, those were discovered to be empirically true under the conditions in planet Earth, right? People weren't doing these experiments up like in a vacuum chamber or up in a really high pressure chamber. They did make attempts to do that, and we'll talk about those historical bases as we go. However, most if not all of these relationships were figured out in what we think of as this ideal gas regime, which just so happens to be about planet Earth conditions. So all of these relationships are what we kind of think of as a limiting law, so they're condition specific. And now we're going to go into a lot more detail uncovering when these conditions no longer apply. So when our gases no longer behave in this perfectly ideal way. Okay, more on that in the coming videos.